welcome. In the time of big data and data-driven decisions and stuff like this, how can we collaborate on data? This is what we're going to learn from Christian. Welcome.
My name is Christian, and I want to talk today a little bit about how we can collaborate on data and why we absolutely need open source to do that. So first, briefly about me, I'm Christian. I love open source. Typically I say I'm from Hamburg, but actually I'm from Schleswig-Holstein, so I just changed that on my slide, and I'm a proud citizen there. So I'm a co-founder of a company called Vacamo. We're just 3 people today, and we're developing an open source software which is Apache licensed. More on that maybe later. But today, I don't want to talk too much about this individual product, but more about the whole ecosystem around data lakehouses and the open source projects in that area. So in order to understand where we really are today with, data and collaborating on data, we need a little history. Maybe first of all, to judge my audience here a little bit, who knows what a lakehouse is? Okay, very few hands. I typically get more. I'll try to explain it as best as I can. Okay, so let's get going. So when I'm talking today, I'm always talking about analytical data, right? So about loading lots of data that we need, for example, to train machine learning models, to do analysis of our performance, about what we typically would do in systems called data warehouses, right? Where we have all of our KPIs and compute all of the KPIs and collect all the data of our company to then have data-driven decisions. Okay, so let's talk about the history of these analytical systems first. And I want to start at the beginning. So briefly, after the Big Bang, we started to develop, relational database systems. Because we had these relational database systems, we were also using them for analytical use cases, right? So we were storing data in them, we were building dashboards on them, we were maybe doing a few analysis using some tools out there. And this was really a good time because databases, they are transaction safe, as we know, right? They have a schema, you have a table, the concept of a table. You have governance and access controls on these tables. So those systems were very robust. However, over time, it wasn't enough to just use relational databases. And they got a little bit under stress. Why? Well, because our requirements changed, right? When we talk about data today in big companies, we want everyone in the company to work with data, right? We don't have this one central team of business analysts anymore who work with data, but we want to share it across our whole company. So we have various different clients, and they all want to work with our data. So because of this, the central compute of our database becomes a problem. The problem of a classical database really is that it is a bundled package where you have storage and compute in the same box, and you need to scale both of them together. Instead, what we would maybe prefer is that we have all of these different clients up here, and we don't have this bottleneck of a compute in between, but instead we can directly access data on our storage. But in order to do that, data on storage needs to be in an open format, and I'm going to come to that in a second. So the problems that emerged were that these classical data warehouses based on big, fat relational databases, they didn't really scale. They became super expensive and so on. And also, they aren't very performant to give data out, right? So you typically connect to a database using protocols like ODBC and JDBC, and it's really time for them to die, at least for analytical systems. These protocols are 30 years old, and that's approximately how fast they are. They are not parallel, right? They are node-to-node connections. They are not parallelized connections. Serial, slow connections. And this is fine, of course, for applications, right? Where you want to update a single row or where you want to retrieve data for your application. But this is catastrophic if you want to extract lots of data from your data storage. So we had many problems, and companies around the 2000s started to look for a solution. And the solution was, let's get rid of this compute layer here, and let's just store our data in an open format on our storage. So imagine CSV on S3, right? Now, of course, that's not a good idea, but we'll come to that in a minute. But what decoupling our compute from our storage brings us is that we now have a super scalable and performant infrastructure because, I mean, storage is cheap and we can replicate storage. It's super fast. It can become super fast. And we can scale our computes, all of our processing engines independently. Because the data is now in an open format in our storage, we can also choose the compute that we like to actually work on the data. Before, we always had to go through this single, compute engine, which is our database server, right? And we were limited to the SQL that this server understood. And it comes with a big cost reduction. So also a lot of advantages, but we're losing these things that the database had before, such as transaction safety and so on. So some people started to develop a solution to that, which is, why don't we take, both of these concepts together? On one side, we have, things that we would typically associate with a relational database system or with a data warehouse, such as transaction safety, schema evolution, governance. And on the other hand, we use the scalability of a data lake, and we kind of get those two together. And the result of that is called the Lakehouse. And the development really started in around 2015, maybe, in the big tech companies of Silicon Valley. So the idea here is that you have still all the data, similar to a data lake, in an open format on your storage. So for example, on S3. Then you use an open table format, and this open table format gives you these things like transaction safety, schema evolution, governance, and so on. And there is one major open source format out there that is making the race today, and that is Apache Iceberg, and this is the little iceberg logo down there. And because it is an open source format, because we store data now in an open source format down here, we can switch and swap any compute engine that we like and work with data. So this is kind of the marketing slide, as I labeled it, right? So this is when you talk to people about lake houses, what you typically see, right? So they tell you that the lake house is really the unification of a data lake and a warehouse, and you get basically the best of both worlds. You get a super scalable system. So Iceberg was originally invented at Netflix. They today have a lake house that is over 1 exabyte of data. They have single tables that are larger than 1 petabyte, and they're able to manage that efficiently with Iceberg, right? Of course, it's also useful for much less data. Like I typically say, if you have more than 50 gigabytes or so in your warehouse, you should think about a lakehouse simply because it saves costs. Okay, so this is the marketing slide. So it's all good if you just have these two components. And the rest of my talk, I want to talk about why this is actually why these two components maybe are not enough, and why you need open source, and why this is actually such a hard problem to solve to openly collaborate on data. So this is another view on the creation of a lakehouse. We used to have this marvelous system that we called a relational database system, and then we used Thor's hammer and smashed it into pieces, and we got out all of these different pieces here, right? And now what we would like to have in our ideal world is that we have all of these things down here shared. So we want to work on the same data, right? But we want switch and swap for our compute engine up here. And in order to be able to have a switch and swap for our compute engine up here, all of these things that we need open standards for all of these things down here, right? So I'm missing a big open, okay. So we need open standards for all of these layers down here. So we started developing those. So first of all, we need an open standard for a physical file system that is super performant, scalable, and that everyone can connect to. And we came up with systems, based on S3 If you're like in one of the hyperscalers, you can also use Azure Data Lake Store, Google Cloud Storage, or if you're on-prem, Ceph, and so on. So different storage systems. Then we need a performant data format in which we store our data. And the format of choice there is also an open source project under the Apache Foundation, is Parquet. Who here heard of Parquet before? Okay, quite a few, so that's good. So Parquet is a super performant column store format in which we can store a table in a file. Think of it as a CSV on steroids. Much faster, much faster. Type safe, so each column has a type. Yeah, and you can store it on a disk. But what a Parquet file doesn't give you is schema evolution, for example. So what do you do if you want to add a column to a Parquet file? Well, you have to rewrite it. So it's not really a table yet. It's really just a file. So next, we needed a table format to group these files together and make a table from it. And there are like 3 different open source projects out there today that can be chosen. There is Hudi, Delta Lake, and Iceberg. And Iceberg is the one currently with the most, drift, or with the most commitment in the open source community. It's a top-level Apache project, and this is why, I'm choosing Iceberg for today's talk, and also why we're developing software in the Iceberg space. So, what is Iceberg, maybe, as a quick introduction? So Iceberg was developed at Netflix in 2017 to exactly overcome the problems that they had, namely of data lakes, right? They had all these files flying around, and they wanted them to behave like a table. They wanted to use SQL and SQL on these tables, on this data, and they really want the reliability and simplicity, of a database, but on files that are on a data lake. So it's a high-performant format for huge analytical tables. I already mentioned how big tables can be that are stored in Iceberg. And since 2018, it has been an Apache project, so a top-level Apache project. And Iceberg today, and I think this is where its great success today comes from, is supported from all major data and analytics vendors, and that's of course only possible because it's an open source project. So going back, the next little piece that we need is a catalog. So it's nice that we have a table somewhere, but you also want to be able to run a query such as show namespaces, right? Give me all the namespaces or all the schemas in my database. Maybe list all my tables. So we also need this additional component, which is a catalog. And as part of the Apache Iceberg project, we also have a catalog. Or we have a catalog specification, let's put it that way. So as part of the Iceberg project, we have an open API specification that defines how a catalog should work. And then there are multiple open source implementations out there which actually implement this open API interface. So there isn't an official solution, but there are multiple projects out there that implement this. And, well, the purpose of this catalog really is to be a single source of truth for table metadata. So an object store is not transaction safe, right? A database is. In a database, you can have multi-table transactions, right? A transaction over multiple tables. But how do you do this with CSV files on an object store or Parquet files on an object store? There is no way. So the catalog is actually the place that ensures that we can have transactions over multiple tables. So it really makes our lake feel like a database. There are many other advantages here to this. This is a quite new initiative that came up, I think, roughly 2 years ago in the Iceberg community. There were other catalogs in the past, but they are now all deprecated. So now we have this layer 2. So we have an open physical storage based on open formats such as S3. We have open data formats such as Parquet, which are then bundled together into formats by open table formats such as Apache Iceberg. And then we have catalogs that follow, an open source open API specification. And this is where most data people stop. So you have the stack from down here to here, and then you can spin up a Docker Compose now, and you can transform your data in your lakehouse and everything. But what most people don't think about is that we also need permissions and identity somewhere, and we need it somewhere central. Because, as I said before, we want to switch and swap our compute engine, and this is only possible if we have a common standard for permissions and for identity. So the goal that we want to achieve with these two components is that we have two different compute engines. We might have, for example, me using a notebook, a Python notebook, but I'm also using a different compute engine, in this case Trino, which is one of the major compute engines that you can use on very large scale data. And this is shared by multiple users. And no matter which way I go and which compute engine I use, I want to have the same permissions on my table. I want to be able to access this table. My scary me here from Amsterdam, he should not be able to access the table, even though we share a compute engine. This is something that used to be normal in databases, and we need the same in lakehouses. So where should we store our permissions for our data? Well, typically, if we look at a database, permissions on tables are typically stored in the database, right? In the compute, in this system. But that's actually a very bad place to put it if you want to switch and swap your compute, right? Because if you store the permissions there, then you can't reuse it in other compute engines. The next option is that you can store it on a physical storage. And that's also a very bad idea. There is a saying that says, secure your data, not your storage. So we don't want to have permissions on S3, on NFS. Instead, we want to have permissions on tables. Next, the next option that we have is, we can store it in the catalog or in a dedicated permission system. And this is what I'm going to talk about now. So we can have a dedicated system for permissions. And this is an area that, especially in the open source field, recently gained a lot of attention. So there are multiple tools that emerged and in the market now that have no other purpose than just efficiently storing permissions for different entities across our businesses. So you might have heard maybe of the Google Zanzibar paper. It's a big paper that was released a couple of years ago. Who of you knows that? Google Zanzibar and relationship-based access control? Okay, a few people. So relationship-based access control is a superset of RBAC and ABAC and other means of access control. And the Google Zanzibar paper is theoretical. Google uses this internally, but there are multiple open source implementations out there. And one implementation is, for example, OpenFGA, a CNCF project. There are also other tools out there that store permissions super efficiently, and they're all open source, for example, the Open Policy Agent. And our philosophy is that you should store permissions in one of these systems. Because if you store permissions in one of these systems, you can enforce them via the catalog, and I'll talk in a minute about how this works. But you can also reuse them in compute engines where you need them or want them. There is one very important point here. So what we're talking about here is sharing permissions across different systems. So we have a permission stored here, a permission for a table, and we want to use this permission in our catalog, maybe in different compute engines. And in order to do that, in order to share permissions, we also need to share identity. Sharing permissions without sharing identity doesn't work. And that is something that, especially in the data world, is a pain, right? Many databases don't support or didn't support this very well for a very long time. And especially if you have this lakehouse now, this modular system where you can, choose the components that you would like and stick them all together, then getting identity right is even harder. I don't want to talk too much about identity today, but maybe sufficient to say that most clients today luckily support OAuth 2 authentication, OIDC, so we can use standard IDPs now also in the data ecosystem. Okay. Well, maybe one word of warning down there. Any system that creates personal access token, client credentials, password are IDPs, right? And we should only have one of these systems in our overall architecture. So it's nice that we can store our permissions somewhere, and we settled that they should be stored in an open way, in an open tool, right? But how can we actually enforce them? So there are like two main methods how permissions can be enforced today. The first way is called vended credentials, and this is part of the Iceberg specification. So the way this works is that we have, the catalog, this metadata layer, and this catalog, for example, Lakekeeper, which is the catalog that I'm working on, we have a compute engine, for example, Spark, and this compute engine is contacting the catalog and asking for data about a table. Now, the catalog checks the credentials, checks if everything's all right, and if it is, it returns temporary storage credentials back to the query engine. Then, these temporary query credentials are used to access the object store, right? So that the query engine can now directly go to the object store to S3 and retrieve data on a very large scale. Typically, a query engine wouldn't be a single node, right? You might have, I don't know, maybe 10, 15, 20 nodes of Spark, and they all access object stores in parallel, because I said before, data can be large, right? So you need to parallelize here. And this gives you, table level security, so you don't have row or column level security, but at least you have table level security here. The second way how you can enforce permissions is using a compute that you trust. So how could this look like? Well, let's say we have a shared query engine here, for example, which is Trino, and then I'm logging into this query engine, which is again connected to my identity provider because I need to share identity, otherwise I can't share permissions. And then this query engine goes to, the catalog in this case, and asks about a table. The catalog checks permissions, both for validity of the token, so authentication, and it also checks for permissions, so for authorization. But because the shared query engine is using the system user, most likely we will have the permission to access a table. It returns metadata and storage credentials, and then the query engine can natively go to our permission system and ask the permission system specifically for me if I'm allowed to access a table. If I am, the data is filtered, so I'm not getting back results that I'm not authorized to see. And this kind of thing is only possible because our permissions are stored in a central system that is not owned by, by a single entity. So, having said that, you need both, right? So you need, with catalog enforced security, you have table level security that works for all kinds of clients out there. But then with query engine enforced security, you also get things like row and column level security, and you can optimize a little bit better in the engines out there. So there are other means how you can secure data, but I think they are a little bit out of scope for today. So I have talked a lot now, and I want to show that this actually works. And so I have a little demo, and I hope that it works. We'll see. As we know, it's always a good idea to have a live demo. So let's see if it works. Here we go. Okay. So I have a little Docker system running now. Actually, I'm running multiple components that make up, this composed system of what is a lakehouse. And I have a shared query engine prepared here. I'm using Trino, which is one of the largest query engines out there one of the largest projects out there to query data, massive amounts of data. And Trino again is also open source. There are also vendors behind that, but you can also just use Trino in an open source way. And this is what I'm doing here. So let's say we have a user, Peter. And with this user, I'm now first creating a schema, finance. And you can already see, like, even though I'm working with lakehouses and potentially very large amounts of data, it really feels like a table here, right? So, and this is all due to Iceberg. So I'm connecting here to Trino with my user. Let's run this. And I'm creating a schema called finance. And in this schema finance, I'm creating a table called revenue. Yeah, and then I'm just inserting a little bit of data here. So I need to log in. I'm using an IDP Keycloak here as an example. Could be any, but Keycloak I can run locally. So I'm logging in as Peter. And the password is Iceberg. So I can log in. Here I am. And something didn't work. Catalog Lakekeeper not found. OK, so probably failed to. OK, a lot is going wrong here. Let's try one more time. Sometimes I have problems with my timestamps. Docker compost. Wait a second. Maybe I just didn't run the other notebook. Here we go. Bad URL. OK. Seems I have some problems. Let's try it one more time just to restart my Docker Compose. Here we go. From scratch. And up. Ooh. OK. OK, something's not right. OK, I won't fix that now. I'll fix that later. It just was a very short demo. Apparently, some of my host got mixed up, but this is not good. OK, yeah, I'll fix that later. If anyone's interested, come to me afterwards. But what we would have seen maybe is that we have one user logging in, creating a table with a shared query engine. And then we have two different query engines, namely Trino and also PyIceberg, with which we query the same data. And we share permissions between both of them, right? So we share permissions between these two query engines on the same data that is on the data lake. And well, this is a big deal. This is something that in these distributed systems that lakehouses are hasn't been possible before. So yeah, with that, let me wrap up a few things. So first, maybe one slide to Lakekeeper. So what is Lakekeeper? As I said before, it's one of the Iceberg REST catalog implementations. It's completely open source. It's Apache license, so the code is yours, basically. It's written in Rust, so we can build a very small Docker image for the central component that you always need when you run lakehouses. We are using a Google distroless image, so it's a really small image that we ship. And we come with security out of the box. So we have OAuth 2 and permission management built in an open way. So we support OAuth and permissions. Lakekeeper is also multi-IDP capable, so you can connect multiple IDPs at once, which can be super handy. So you might have Kubernetes workloads, for example, working with data. Then you want to use native Kubernetes service accounts and want to authenticate them. But then you might also have, OIDC and OAuth capable identity provider for human users. And we can run both of them simultaneously. OK, so we don't have too many data nodes here, so maybe this doesn't pull too much, but we're happy to discuss this in the break. Yeah, and with that, I am done. So my core message today is that open lakehouses are possible today with 100% open source tools, including governance. For a long time, governance was the missing piece, right? You could get all of these individual pieces, but permissions and access controls, that was something that you needed, a big vendor for, that you needed a platform approach for to secure your data. And today, this is no longer true because we have good enough open source tools in the permission management in the catalog ecosystem that allows us to use, well, as I put it here on the right, we use one identity provider, one source of truth for permissions with different compute engines, and some of them are even shared between users. And all of that is 100% OSS under Apache or similar licenses and can be used today. So for the demo that didn't work, you can try it yourself. The link is here. And then, yeah, otherwise, this is the link to our GitHub repository. If you like what we're doing, give us a star. And then I'm open for discussion.
Might be a pretty small question, but how or which part of the system handles something like concurrency, for example? Or are we assuming that we're not really writing data, but more of accessing data?
So, that's a good question. So, okay, so what's handling, so with, there are two answers, I guess, to that question. So the first is, what happens like if someone writes and another one reads, right? What makes sure that nothing breaks? And the answer is the catalog does, and or the table format under the hood does. So in Iceberg and in all other Lakehouse formats, a transaction works in a way that like everything you change in the table, you add a file. So for example, let's say you delete a row, and you add a file saying you delete a row. Or maybe you have this Parquet file which contains 10,000 rows, and you want to delete the last 50,000 rows. Then you read that file. You can't modify it. A Parquet file is immutable. You modify that file, you remove the rows that you want to remove, and you create this new file. And then you do all of the processing until you're done. And after that, you tell the catalog, I am done writing. Please create a new snapshot. And the catalog will make sure that the changes that you did, this is called like optimistic concurrency control, that the changes that you made are still valid, right? That you don't like break anyone else. But by this you even have like native time travel and history of a table because you keep all the past snapshots. Every operation you do always adds a file, so you have the history. And by that, you don't break readers. So if a reader is already reading a table, the reader is reading a single snapshot, which is comprised, of multiple Parquet files in the end. And a writer doesn't get in the way, it just creates a new snapshot. Of course, eventually you have to clean up your table, and there are procedures to automate this away. But yeah, this is how this works. Okay. Okay, any other questions?
Hello, first of all, nice talk. I'm not a data guy, but coming here, for some reason, I saw the announcement of Duck Lake. I think it occupies the same space as Iceberg. And
yeah. It does, yeah.
It seems a bit simpler, and I would like to know your opinion because I'm not familiar with all of this. So
yeah. So it's an interesting approach for simpler problems. So like I'm not super excited about this format for two reasons. I think they made two mistakes that have been done in the past that are completely avoidable. So there is a new format similar to Iceberg that just came up, and the problem. So let me go to these two problems. So the first problem is it's a single vendor approach, right? There has been actually another project in the past, which is called Delta Lake by Databricks, a huge billion-dollar Silicon Valley company, and they developed a format and called Delta Lake. It essentially did the same thing as Iceberg, but it wasn't 100% open source. They kept some of it proprietary. First mistake. Second mistake, it was controlled by a single company, namely Databricks. And this is why the complete industry rallied behind Iceberg, because they said, well, they are doing something I don't have any control over. Yes, the code is open source, but I don't have any influence over the project, so I want to use a different project. I want to use Iceberg. And now with Iceberg, we have all major players in the industry rallying behind this format, and we have a very active, diverse community that is developing the standard forward. And of course, because it's an open source project, it might be slower than having, one guy saying, I want this feature and merging the pull request. But then at least it is super stable and it is super interoperable. And this is the core feature of Iceberg. And Duck Lake, again, is open source as well. The code is open source as well. But there is one company controlling it. And so I wonder how many people rally behind this. So this is the first thing. So it's not open enough. The second problem is that it uses a relational database as a catalog. So also Duck Lake, because it solves a similar problem to Iceberg, needs a catalog where metadata is stored, where you handle, for example, this transaction safety. Now, if you use a relational database there, this catalog needs a lot of business logic behind it, right? It's not a simple piece of code. It needs quite a bit of code, also the Duck Lake one. And because Duck Lake uses SQL as an abstraction, we have the problem that now we want different ecosystems, different query engines written in different languages interface with this catalog. But this original catalog from DuckDB was implemented, in C++, and we only have this one implementation. And this is a problem if you want to have a diverse ecosystem. Then SQL is not the best abstraction that you can choose. Iceberg actually also had a JDBC catalog in the past. It was implemented in Java. And now every time you had a client that wanted to read this open table format, it has open in its name, it needed this jar to access the catalog, right? And injecting a jar is something absolutely awful, and then choosing the class that you need to access the catalog. And that's maybe something that you can do in other Java-based query engine, but try that with, a Rust-based query engine, C++-based query engine, or Python, or whatever. It's a pain. And this is why Iceberg actually deprecated their JDBC catalog, which did exactly the same thing as Duck Lake, and went forward to an abstraction layer that is much more compatible between heterogeneous client ecosystems. And this abstraction layer is a REST specification, because everyone can send a curl request and everyone understands JSON. So it's a much more open approach. So these are, I guess, my two biggest critic points there for Duck Lake. But for someone who's deep in this ecosystem and uses DuckDB anyway for everything, this should be fine. But it's not interoperable. Okay, that was a longer answer probably than it should have been. Okay, more questions.
Question?
Okay.
Then I would say thank you very much, Christian.